Good morning and once again welcome to my YouTube channel, Pearson and Excel International Maths. And I want to introduce topic or chapter number 5 in Pure Mathematics 4. And we are looking at page 51. And this is topic called differentiation. And the very first subtopic of that topic is parametric differentiation. And I want to explain what is parametric differentiation. We know when functions are defined parametrically, you can find the gradient at a given point without converting into Cartesian form. You can use a variation of the chain rule. We are told that when a function is defined or expressed parametrically, you can find the gradient of the function at a given point without really converting them to the conventional or the Cartesian form. And of course, if we are told that if x and y are given as functions of a parameter t, then we know by chain rule dy dx is given by dy dt multiplied by dt dx. This is of course part of the chain rule, and it follows that when you're talking about dy dt multiplied by dt dx, and this is dy dx, of course you can also obtain dy dx or dy dt. For example, you can make any of this the subject of the formula. For example, if you want to get dy dt is of course this over this, that is dy dx divided by dt dx, which is by extension dy dx times the reciprocal of the divisor. Please remember, when we divide by a fraction, is the same as multiplying by its reciprocal, so dx dt. So anytime we're having dy dx times dx dt, we get dy dt, and we can also get dx dt we can make anything the subject of the formula. For example, if we want to make dt dx the subject, dt dx is given by dy dx divided by dy dt, which is by extension dy dx times dt dy. That is true. And of course, when you want dx dt again, it's the reciprocal of what you find here. So having said that, it is important to look at example 1, just example 1. And example 1, we are told find the gradient, find the gradient at point P, with coordinates where t is equals to 2 on the curve given parametrically parametrically by x is equals to t cubed plus 1 and y is equals to t squared plus 1, of course, where t is a real number. This one, you can see x is expressed parametrically and y the same case. So we can desire to get dx dt, which is very direct, which is 3t squared, and this is t cubed plus t, not plus 1, plus t. So the differential is 3t squared plus 1. And dy dt is 2t, and that is the differential. So in other words, when you're talking about, you want to talk about dy dx, or rather the gradient or differential, is to be given by dy dt times dt dx times this is dy dt times dt dx. We have seen it here, dy dt dx. Of course, dt and dt are supposed to cancel out, and we are left with no, this is let me take that again. Dy dx is easily dy dt multiplied by dt dx, such that the dt and the dt will cancel out, and of course we'll be left with dy dx. So in this case, what is our dy dt? It is 2t times dt dx, and I would want to say that dt dx is the reciprocal of dx dt, which is times 1 over 3t squared plus 1. So basically we are talking about 2t over 3t squared plus 1. At that point, we are told that but t is equals to 2. So dy dx is 2 multiplied by 2, everything over 3, 2 squared plus 1, which is 4 over, this is 12 plus 1, which is 13. And that becomes the gradient, and that becomes the gradient of, so the gradient at t, so the gradient at p is 4 out of 13. Please take care of this part. Ignore this part, just ignore this part, and let us just concentrate on that part. It is also possible that you would have said that dy dx would have been given by dy dt, you divide by dx dt, and this is what has given birth to dy dt times the reciprocal of the divisor, which is dt dx. Either way, as we move forward, we will be able to evaluate further what is expected of us. That is just like an introduction of differential parametric differentiation. Moving forward, we shall see other examples, and let us work together. Subscribe to my YouTube channel, Pearson and Excel International Maths by Mr. Kamotho, and let us learn together. All right.